So this section is about text representation, and I'm going to let you know some basic approaches for the text representation. So today we are going to learn about those things. There are two methods that we will learn. First is the count-based methods, and it is about the one-hot encoding, pack of words, and TF IDF. And the other is about distributed based method. So it is about the word to fact, which is skipgram and CPOW, and glove and fast text. So the count-based methods. What is count-based methods? In NLP, in the natural language processing, we have the word text representation. So text representation serves as a cornerstone for various machine learning tasks. Before we do the machine learning, we need to deal with the text, how we can represent it before the machine learning. So the text representation, usually we also call it as the feature engineering. So some of the, if you learn about the data mining, or if you learn about the machine learning, you will know about the feature engineering. So one of the name for the text representation is feature engineering. And there are some methods for the text representation, and one of them we call it one-hot encoding. Okay, so it is the common approach in the data mining, in the machine learning, or sometimes we call it OHE. So in the one-hot encoding, each word in the vocabulary is represented as a binary vector. Binary means 0, 1. Okay. So for example, I have these 3 sentences. I love this movie. This movie is terrible movie. The plot is confusing. So we can change this one into a binary vector like this one. The column name means the word that we want to present. And then the number means whether the word exists or not exists. So the first sentence, we have I love this movie. So we have this movie love. So if we just have this as the one-hot encoding, then we can present one as this kind of vector, 0, 0, 1, 1, 0, 0, 0, 1. So this is the vector for this one. And then the second one, we have this vector, and the third one, we have this vector. So everything will be in 0 or 1, exists or not exists. The one-hot encoding is good and it is common, and this is simple. Okay. Simplicity, simple, because it imposes an arbitrary relationship between words, but it fails to capture semantic similarities. Semantic means we cannot understand the meaning. So the meaning means other limitations. We have no semantic information. For example, the similar words have no common representation. For example, if I want to say hotel, motel, So hotel and motel actually they represent the same semantic. But when you change this one to 0 and 1, if there is a word motel, if there is a word hotel but no motel, it is 1, 0. But actually they are the same. Or if you have the word hotel and motel at the same time, then even though they are the same, but it will be in the different pattern. The second limitation is the variable text length. The variable text length means it depends on the sentence. It can be large and varying in dimensional factors depending on the purpose. So if you see from the previous example, now we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 columns. But when the sentence is long, and if the words are varied, it means there will be a longer columns. And if the column is variable, then it means it will be difficult for you to do the machine learning because every time the variable is changing. And there are out of probability. We call it OOV. So the OOV means it is related with the sparsity problems. Factors filled with zero. It means if you look at the example, there are many zero. So zero means there is no word on this sentence. If this one is small, it is fine. But if it is huge, if it is large, then we will have an issue, what we call as the out of probability. So that's why we call it, this is the sparsity problems or factors filled with zeros. So there are other kind of representation. We call it back of words. And sometimes we call it as the count factorization. So count means we have the frequency. Okay. So back of words, or sometimes we call it as BOW. It is a common NLP method that is used to represent text documents of varying length into fixed length vectors. So if we have the one-hot encoding, we still have some varying length, but in this POW, we can have a fixed length. So the length will be fixed, and then we can put it as the features for the machine learning. Now, if you look at the one-hot encoding, OHE, it is binary. Binary means 0 or 1. But for the BOW, we use the frequency. So the frequency means how many times the word appears. So this is an example of BOW. As you can see, there is a number 2, like this one. It means it shows how many of the word movie appears in a sentence. Yeah, other word just show 1, but this one show 2. It means the word movie appears 2 times. So the process of the POW, usually we will have a corpus. We call this is a corpus. A corpus means the collection of text. So this is the text that we saw before. I love this movie. This movie is terrible movie. The plot is confusing. So we will do the first step, which is tokenization. You already know the tokenization. It is from the text pre-processing. We already learned last time. With the tokenization, we will split what every of this word. I love this movie. So this is one. This is one. This is one. This is one word. So for every word, we will put it into the word frequencies. So we will count how many frequency of every word. And after that, we will input the data. So the encoding will represent something like this one. The encoding will represent something like this one. So after we count the frequencies, then we will do the encoding. Of course, when we do the tokenization, there will be some kind of process like what you already learned before. In the text pre-processing, we will have the tokenization, and then we can do the make the text as the lower case, and then remove the white space, and then we can remove the stop words, and so on. So if there are some unnecessary words, we can remove it. And we just look at the important words for the next process. But the back of words still have issues. These factors ignore the grammatical structure of sentences. And it also ignores the orders of words. So grammatical, like in English, we have the grammar, 문법. And then the order of words, so the sequence, it is ignored with the back of words. So for example, I love my parents, comma, Mother Teresa and Barack Obama. If you understand in English, so the audience might think that your parents are Mother Teresa and Barack Obama, because there's only one comma here. So this grammar cannot be detected with the back of words. So the correct one should be something like this one. I love my parents, Mother Teresa, comma, and Barack Obama. So in this case, people will understand that, okay, I love my parents, Mother Teresa, and Barack Obama. There are three objects in this case. But when you do with the POW factor representation, you will do something like this one. So everything is only the numbers. And these numbers cannot represent what is the sequence, what is the next word, and what is the previous words. So this representation is the basic representation, and usually people will use this one as the initial states for the machine learning. After we learn about the POW, in many cases, we will use the n-grams. So n-gram is a continuous sequence of n items. So n refers to the number of items in the sequence. So this n can be 1. If it is 1 gram, then it means the unigram. unigram is a sequence of one item. If n equals to 2, if n equals to 1, then it is unigram. If n equals to 2, it is bigram. It is a sequence of two items. If it is 3, if n equals to 3, then it is a trigram. It is a sequence of three items. And so if I have the word I love this movie, so the 1 gram is I love this movie. If we want to check the 2 gram, it means there are two words. So I love this movie. If it is 3 gram, then I will have three words. I love this movie. So we can present the text as the n-grams. Now, we use n-grams to predict some kind of sentence. So we can use the n-grams to predict the completion of a sentence. So I will just show you the very simple one. If you go to the search engine like Google or Naver, if you look at the search text box and let's say you write what is, so there will be some options given by Google. What is my IP? What is project 2025? What is this song? What is love? What is AI? What is weather today? And so on. So how Google can understand this one? This is based on the frequency. This is based on the probability. What is the most possible sentence that you will create? What is the most possible words after what is? So for example, if I have this word, please turn off your cell phone. Can you predict? We know that this word most probably is phone, because cell will follow with the word phone. But what about this? Your program does not. There are many possibilities. Okay? We can say your program does not run. Your program does not work. Your program does not proceed, and many things. So we will check about the probabilities, and we can use the n-grams. It means we can estimate the probability of each word given the prior context. What is the prior context? The prior context means what is the previous word? I want to know the probability if the word is phone. I want to know the probability if this word is phone, given that the previous text is please turn off your cell. So if I know this probability and the probability that this word followed by this word, then we can have a confidence that this word will be phone. So we will check the high probability of this word. So the n-grams, the number of parameters required grows exponentially with the number of words of prior context. The prior context means the word that you have before. For example, you have the Korean words 안녕하세요, 만나서 진심으로 반가워요. Then, if we want to make a model with the n-gram, so we can have the unigram. For example, I want to know what is the probability that the word 반가워요 appears. If I use the bigram, So I want to know what is the probability of the word Pangawoyo given by the previous text. So n minus 1. N minus 1 means the symbol. So it means there are 2 items. How about trigrams? The trigrams, if I want to know the word Pangawoyo appears, what would be the probability if there are 2 previous items? Okay, the 2 previous items means the Manaso, Chinsilu, and so on. So the n, it's not limited to 1, 2, and 3, but it can be 4, it can be 5, it can be 6, and so on. It depends on the context. It depends on the application. Then we can have something like this. If it is a trigram, I want to know the probability of Pangawoyo given the text as Manaso Insinu. Then it is the count of the word Manaso Jinsimro Pangawoyo. So how many times this word appears divided by the word Manaso Jinsimro. So the mathematical equation for the n-gram, if it is a bigram, okay, so we can have the conditional probabilities. Conditional probabilities. It can be estimated from the raw text based on the relative frequency of the word sequence. So I want to know the probability of the word at the position n given by the word in the position n minus 1. So we have the count, okay, the count where the word in the position n minus 1 and the position n divided by the word in the position n minus 1. Or if we want to make it more general, then we can have the n-grams. So the n-gram means this is the probability of the word in the position n, and we want to know what is the word in the position from n minus 1 until n minus big N plus 1. So the general formula will be that. So to have a consistent probabilistic model, we can append a unique star. So sometimes we put this one S as the unique star and N. So this with slash S to represent a unique N symbol to every sentence and treat this as additional words. So what does it mean? Let's see with an example. I have 3 words. S, I am Sam, N. Okay, so this is to say this is the starting of the sentence and this is the ending of the sentence. The second sentence, we have another word, Sam, I am. The third sentence, we have I do not like green eggs and ham. So how we can calculate the bigram probabilities? So let's see here. The bigram probabilities. I want to know what is the probability of I appears given the S. So S means the starting. So I want to know what is the probability I will be at the starting of the sentence. Okay, based on this data, there are 2 I after the S among 3 sentences. So we have I I. So 2 out of 3, we can see that I is the starting of the sentence. So we have the probability is 0.67. Now I want to know what is the probability of the word Sam appears after the starting, or I want to know the word Sam at the beginning of the sentence. So how many Sam do we have? We have 2 Sam, given that we have 3 starting sentences. So among the starting sentence, only one appears at the beginning or appears after the S. So it means 1 over 3. If I want to see what is the probability of M given I, then you will see the word M, there are 2, and those M are after I. But we have I, there are 3. So 2 out of 3, we can see the word M followed by I. So we have 0.67 of the probability of the M given by I. What about probability of 2 given I? So we have only 1 out of 3 of I. Now, if I want to see the probability of Sam given the word M, what is the probability? We know there are 2 M. So there are 2 M, and then how many Sam after the M? So we can see there is only 1 Sam after M. So we have 1 out of 2 M. And then this one we have the same. I want to know how many of the word Sam, which is I want to know the end of the sentence followed by the word Sam. So after Sam, followed by the end of the word. After Sam, followed by the end of the word. Then we can see there are only 2 Sam, and only 1 is after the word Sam. So it is the probability is 0.1. So here's a question. What is the probability of M given the word Sam? So how many Sam do we have? We have 2. After Sam, how many of the word M appears? Nothing. So it means 0 divided by 2, and it is 0. So the probability is 0. Okay. The other kind of the count-based method, we call it as the TF IDF. So TF IDF means term frequency and inverse document frequency. So term frequency refers to the document of occurrences of word W in document D. If the value is 0, then it means the word does not appear in the document D. And we have the inverse document frequency. The inverse document frequency built upon the term frequency by inversely weighting words that appear frequently across all documents. Okay, so we will check this one based on the example. The inverse document frequency, or the IDF, it diminishes the importance given to words that are common in general rather than to one specific document. So if it appears in many documents, so it is common. But we want to find something specific, something that is only in one or two documents. We can use this formula to check the TF. TF means the term frequency of keyword I in document J. IDF is the inverse document frequency calculated with the log n. N means the number of documents, and ni means the number of documents from n in which keyword I appears. And the TF IDF will be calculated by the TF IJ, which is from here, multiplied by IDF I. So let's see. We have three documents. So D1, music is a universal language. D2, music is a miracle. D3, music is a universal feature of the human experience. So this will be the result. So we will check how we can calculate each of this. First, we will calculate the TF, the term frequency. The term frequency, we call it frequency, means how many times it appears in the document. So the formula will be the number of times the term appears in the document divided by the total number of unique terms in the document. So for example, I have a cat. My cat is very cute. I love my cat. So what is the meaning by unique terms? Unique terms. Unique term means something which is not in the duplicate. No duplicate of the words. We can say that the TF of the word cat is 3 divided by 9, or 0.33. Why? If you look at this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, so we have 13 words. But why we divide with 9? Because we need to make it unique. Okay. Unique means there is no duplicate. So the number of unique words in the above document is 9. What are they? The word I. Okay. So we have I and I. We have 2. So unique word will be only I. Have. And then only one cat. So how many cats appear? We know there are 3. But we need to understand the unique terms. The unique term is only one word. My. So how many my appears? 1, 2. So we need to make it as a unit, only one. is very cute and loud. Okay. Then we can see there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 unit terms in this sentence or in this corpus. So the TF or the term frequency for the word cat will be 3 divided by 9. So this is the same with this one. So music is a universal language. So how many unit terms do we have? 1, 2, 3, 4, 5. Okay, then it means every word, the music is 0.2, is 0.2, 0.2, universal 0.2, language is 0.2. What about is? The music is a miracle. So because there are 4, then music is 0.25, is 0.25, 0.25, miracle 0.25. Here is music is a universal feature of the human experience. So every word is unique. So we can just divide with the 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 over 9 for the music, 1 over 9 for is, 1 over 9 for and so on. So we can get the term frequency. Next, we will check the IDF. The IDF means the inverse document frequency. Because we have only 3, so let me show with another document like this one. So we have the 5 documents: document 1, document 2, document 3, document 4, and document 5. And let's check the word water. So you can see out of 5 documents, only 3 documents contain the term water, like this one. Regular exercise is the key to improving our all fitness levels. Water, okay, there's water here, covers blah blah blah, and then document 3, drinking water, and blah blah blah. Document 4, there is no water, and document 5, we have water. So it means there are 3. Okay. There are 3 out of 5 documents. So to calculate the IDF for the term water, we use the formula IDF. The word IDF, we know the formula. It is a log function, which is the total number of documents. So we have 1, 2, 3, 4, 5, and then divided by the number of documents containing the term water. So we have the log 5 from all documents we have divided by 3. Okay. So the IDF is about 0.22 for the word water. So we can apply the same for this example into the document that we have here. So music is a universal language. So music, how many music appears in the documents? We have 3. Okay. Then we can just make the log function. There are 3 documents, and among the 3 documents, the music appears in all documents. So 3 divided by 3, and then we use the log. So it will be 0. Log 1 is 0. The same with this. The same with what about universal? The universal appears in 2 documents. So we have log. Among the 3 documents, we will see it in the 2 documents. Then we have log 3 divided by 2. So this is the idea. And so on. Okay. And after that, we will get the TF IDF. What is TF IDF? We will just multiply the TF of the document 1 multiply with the IDF. 0.2 multiplied by 0. So we have the TF IDF document. TF document 2 multiplied by IDF. Every number multiplied by 0 will be 0. This will be multiplied with IDF, and every number multiplied by 0 will be 0. Is also will be 0 because the IDF is 0. Will be 0 because the IDF is 0. But what about the universal? Universal appears in the document 1 and in the document 3. So the TF of document 1 is 0.2 multiplied by 0.176. So this is the result. And what about the TF in document 3? 0.11 multiplied with 0.176, and this is the result. And after we have this one, we will present this one into a factor. So we have the factor as like this. So the document 1, the TF IDF factor will be 0, 0, 0, 0.035, 0.095, 0, 0, 0, 0, 0, 0. So in this case, in the document 1, we can see there is a specific word about universal and language that is important. In the document 2, we have miracle as a distinct word. And in the document 3, we have universal of the feature experience humans. So those are the distinct words in the document 3. So using these TF IDF factors, then we can do later with the machine learning. We can use these features as the features for the machine learning, and we will check what is the importance of these features to make something like text classification or text clustering and etc. So this is the Google Colab. Maybe I will. Okay, let's have a break. I will continue this Google Colab and the remaining after the break.